So I want to talk about joint work with Andreas Strombergsson, kinetic transport in quasicrystals. And the way we want to model this is using the classical Lorentz gas. So I'm going to talk only about classical mechanics. My final aim is to quantize everything and also understand the quantum world, but that'll be for the future. So the Lorentz gas, as many of you know, consists of an infinite fixed array of spherical scatterers in which you have a gas of non-interacting point particles that just bounce off these scatterers. And if we model them by hard spheres, we just have the usual elastic reflection. But all I'm going to say, our theory also applies to soft potentials, like muffin tin potentials. The important assumption is that they have compact support and that they're dispersive. Okay? Now, Lorentz' original idea was to model transport and matter, and he followed the same heuristic arguments that Boltzmann had developed to postulate a macroscopic transport equation in the limit of a low scatterer density. So our scatterers are spheres of radius rho, and that's supposed to be small. So the first question you ask is, what is the mean free path length? And a simple dimensional argument shows you that the mean free path length obviously will grow, and it will grow exactly at rho to the minus d minus 1, which is just the cross-section of each scatterer that you see. So to obtain a kinetic transport equation of Boltzmann type, what you have to do is to look at the dynamics on the scale of this mean free path length. Right? If you don't rescale variables properly, you either see nothing, you just see free motion because you'll never hit anything in finite time. And if you look at longer time scales, that's also an interesting question, you would see possibly things like a central limit theorem, diffusion. But we are interested in the so-called Boltzmann-Grad limit, so that's exactly rescaling your time and position coordinates by the mean free path length. So we introduce these macroscopic units here by just rescaling in the way I described it. And then one expects for an initial particle density f here, so we just take some probability density f in L1 that models our initial particle configuration. And we are interested in the evolution in time, so we denote this by ft rho, and the question is, does this converge weakly to some sensible answer? Is there a limit of this? And then if there is a limit, how can we describe this limit? And here is the linear Boltzmann equation, which we also call Kinetic Lawrence equation. That's the equation Lorentz wrote down in his original paper. And it consists of two terms. Here's the transport term on the left-hand side. So if the right-hand side would be 0, this would just be the evolution of a non-interacting gas cloud. And the interesting term here is the collision integral, which relates the velocities before and after the collision by the differential cross-section. OK, and the main hypothesis in deriving this equation is that consecutive scattering events are independent of each other. And this is why here you only see the differential cross-section of an individual scatterer appearing in this limiting equation. Now, it took a few years, around 70 years or 60 years, for this to put on rigorous footing. And this started off with a famous work by Gallavotti, who assumed that our scatterers are random, more precisely. They're sitting on the points of a Poisson process. And he proved that in probability, our particle density converges. Spohn extended this to more general random scatterer configuration. And an important result here by Bolderghini, Bonimovic, and Sinai proved that the convergence holds for almost every scatterer configuration. So not just in probability, so not just the expectation value of our ft converges, but converges actually almost surely.
And these authors also verify the Boltzmann equation.
Yeah. So that's exactly the proof of the convergence, and the limit satisfies the linear Boltzmann equation. There are papers that ask the analogous question in the quantum setting, and that's exactly what I'd like to generalize for what I'm going to show you today. Spohn, Erdős and Yau, and Erdős and Eng proved results here in the weak coupling limit, and what is of interest to us here in the low density limit. Okay, so when your scatterers are random, we get the linear Boltzmann equation. So the obvious question is, what happens when your scatterers are not a typical realization of a Poisson point process? And the extreme case is, of course, the periodic Lorentz gas, which in ergodic theory served as a fundamental model to study diffusion when you fix the scatterers. But here, of course, we want to shrink the scatterers because we're interested in the possible kinetic transport that will emerge in this limit. So here's the typical example of a lattice. It's just the square lattice, and we're following our trajectories here. So we ask exactly the same question as before. So I just remind you, we're rescaling all the units as before by the mean free path length. So we measure everything in units of the mean free path length and the mean collision time. And a few years ago, with Andreas Strombergsson, we proved again that if you look at the evolution of a microscopic particle density that extends initially, so it's measured again in the macroscopic coordinates, so it extends over units of the mean free path length, that indeed there is a limit for the dynamics in this scaling. So in order to formulate this, let's define a time evolution operator here that propagates our initial density, L rho of t. And what this theorem says that we weakly converge to a limiting process that is described by this linear family of linear operators L of t. And the big surprise here is that this family of operators LT don't form a semigroup. This might be surprising because, of course, for each fixed row, we have a semigroup. That's obvious. Hamiltonian dynamics generates a semigroup. Somehow the information is lost here. And the resolution of this seemingly paradoxical phenomenon is that to recover a semigroup, you need to keep track of more data as you go into the limit. And this data is the time until the next hit and the velocity after your collision. Now these, of course, microscopically are functions of Q and V, right? In Hamiltonian dynamics, everything is determined by your position and your velocity. However, as you go into the limit, these two variables become independent. That's what we can prove. And in fact, if you now keep track of a density in this extended phase space, you do get a linear transport equation that looks like this. And when you want to recover your original particle density, you just integrate out those two auxiliary variables. Yeah. It's just where the scatterers are sitting. It's the Lorentz gas. It's just not random. periodic now. Okay, so
Where's the difference in the Boltzmann? You said that you had to keep track of more information. So what's the extra piece?
the extra piece is the time until the next hit. So you look at your test particle and you just you look forward. Yeah, you could formulate the same thing looking backwards. It's equivalent, but it's nicer to look forward. And you look at the future velocity after the next hit. That's v plus. Yeah, it's easy to study, and you can control the rate of convergence to equilibrium and these kind of things.
So the fact that you don't have a semigroup anymore comes from the fact that you've integrated these out. Is that what happens?
That's right. So the projector doesn't commute with the time evolution. And this perplexed me in the beginning. Now, when so in fact, you can view this equation, which in fact is the Fokker-Planck Kolmogorov equation of the associated Markov random flight process. You can view this equation as a generalization of the linear Boltzmann equation in the following sense. If you look at the right-hand collision integral, there is this transition kernel here, which is a specific function in the periodic scatterer configuration, which we've calculated. Now, if you have a random scatterer configuration, you can do the same thing. You can calculate this function, and it'll look like this. So in the random scatterer configuration, the probability of hitting the next scatterer after time t will be exponentially distributed, e to the minus t. And it will be independent of anything else. So you can write down this transition kernel. I mentioned that the velocity distribution is given by the differential cross-section, so you throw this in. And then if you make this ansatz here, in this equation, you recover the linear Boltzmann equation for gt. So everything's consistent. Okay. Now, that, of course, then raises the question, well, what can we say about other scatterer configurations? And that's my program that I'm working on right now, is to find a large collection of examples. I'm going case by case, okay, where you can prove the same thing. And today I'm going to talk about quasicrystals. Yeah. I'll go there. So before I'm going to go to the quasicrystals, I'm going to show you how this works in the periodic setting, because that'll be easier then for you to understand, also appreciate the difference in the quasicrystal setting. The key idea will be always the same. There's no new idea from the periodic setting. In a sense, if you're mean, you can say we're just turning the handle of our big machine. But you'll see some beautiful mathematics will come up in this. So the key theorem to prove the previous equation is to study the first n segments of your random flight. So this is your particle shooting off from a specific point in a random direction. And you want to understand the joint distribution of these path segments. If you do this, then your limiting flight process will just be moving with unit speed along this path. That will be a Markov process with a certain memory, and from that you can then derive the integral differential equation that I had on the previous slide. Yeah?
Maybe you said it, but I guess it's important that your initial distribution is a smooth density. I mean, that's somehow
Smooth density in the velocities.
only in the velocity.
Only in the velocities. So the strength of our approach is actually that we can fix any position and we get this limit theorem. But that's a little bit of an overkill. To actually prove the physical theorem, we want our particle density just to be L1. We can prove it, not L1 in phase space, but we can actually prove it by having a delta mass on the point and then being L1 in the velocity space. But that's the formulation. That's sort of the physical formulation. We have a random initial point with respect to some measure lambda. That's just a measure whose density is our particle density. And this theorem tells us that the subsequent path segments in our random process converges to something. And this something factorizes nicely, and from this you see it's a Markov process with memory too. I'm not going to prove this theorem to you. I'm just going to do the first step, and that's the first collision, the first hit. If you want to prove the full theorem, you have to then keep track where the particle is hitting. You need to make sure that your outgoing distribution of the new velocities is regular enough, because it'll depend, of course, on a lot of things that happened before. What we need to show is that these things, in fact, show this loss of memory that leads to the Markov property. But I'm not going to talk about that, because the main idea, everything you can already see in this problem, everything else is technical. There's been a lot of work on this before, starting from a beautiful paper by Polya on visibility in a forest, both random and periodic. And then the question of the distribution of the free path length for a random velocity was completely solved by Dahlquist, who wrote down the formula but didn't prove it, and then Boca, Cobelli, Zaharescu, and Gologan. They completely solved this problem of the all periodic. Now everything's periodic. In the random situation, we know it's exponential. That follows from simple probabilistic arguments. In higher dimension, very little was known. The main result here was work by Bourgain, Golze, and Wennberg, who proved that if the free, so proved basically upper and lower bounds on the tail of the distribution of free path lengths, not proving that it exists in the limit, but just giving upper and lower bounds. And I'm going to show you now the key ideas in this joint work with Andreas Strombergsson, where we proved the existence of the free path lengths in any dimension and also calculated precise tail asymptotics. So, but here is the main idea. So in order to explain to you what we're doing, I need to introduce the notion of a random lattice, because the distribution of the free path lengths will be the distribution of a certain random variable that is a function of a random lattice. Every Euclidean lattice of covolume 1, so covolume 1 means the fundamental cell of your lattice has volume 1, can be parametrized in this way. You start with your cubic lattice, and then you shear it and turn it, rotate it. So in other words, you apply some linear transformation that's volume preserving, because you want to preserve the covolume, so that's SLDR. And then you observe that your initial cubic lattice is invariant under SLDZ. So that's the stabilizer, and in fact you can show easily that the space of such lattices is parametrized, so there's a one-to-one correspondence with a point in this homogeneous space. And now Siegel showed us that that the harm measure from SLDR projected down onto this homogeneous space is finite. Minkowski is finite, and Siegel calculated. He calculated? I thought Siegel did that. Thank you. Can always learn something here. Okay. And so we have a formula for the probability measure, which is now a SLDR right invariant probability measure on this homogeneous space. Now, because we want to also shoot off not necessarily from a lattice point, but from some other point, we'd also like to shift our lattice so that point where we shoot off from becomes the origin, and you can define analogously a space of affine lattices. I'm not going to go through this. The upshot is that now the new Lie group that we need to work with here is a semi-direct product of SLNR and the group of translations. Here are all the definitions. Everything's the same. You again get a probability measure on this space, which is invariant under your group ASLDR. And so here you see how this comes in. This is the theorem that shows that the distribution of free path lengths has a limit. So I'm going to denote by tau1 the free path lengths corresponding to an initial point at Q and V. Now Q is fixed and V is random. And we assume that V is random with respect to any nice probability measure on the space of direction. So nice means absolutely continuous with respect to Lebesgue. Here's the limit. And we have a formula for this limit in terms of random lattices. So if we shoot off from the center, from a lattice point, we get one answer. And that answer is that the distribution, the probability that our free path length is bigger than xi, is given by the probability that a random lattice does not intersect with this cylinder. If we shoot off from a generic point, and generic means this, no rational multiple of a lattice point, we get a different distribution, and that's the probability that a random affine lattice doesn't intersect with the same cylinder. So let me explain to you why this is so. You have a question, Tom? So the cylinder is just a cylinder. It's extended in one direction, and its cross-section is just a hyperdisk in d-1 dimension. Yeah, it's a rectangle.
But did they ever recognize the answer as
No.
in the space?
No. No.
How did they describe their measure?
They used continued fractions, and they just calculated it. They calculated an explicit formula.
They actually did some integrals.
Yeah, they did integrals, and they got a beautiful formula for it. Okay, but to me,
But they never recognized it.
that's right, and no one else did before. Because once you have this translation, I'm going to show you the argument is very simple. You could have, without proving anything, you could have conjectured that that should be the answer. I know, which you taught me how to do. Okay, so here's the idea. And I'm going to look at the case when we shoot off from the center of a scatterer. Okay? And so now we are interested in the probability that we're not going to hit anything until this time we scaled. So this is, again, that's the mean free path length, so the mean collision time. And so in other words, we're interested in the set of directions for which this ray doesn't intersect any sphere. Now, up to a small error, this is the same as asking, is there any lattice point in this cylinder? Now, the little error comes in because this cylinder should really have caps here. But because we're interested in the limit of small rho, we can neglect this. Of course, you need to prove that the probability that there's anything in there is small. But that we can do. So now it becomes a lattice point question. We are interested in the set of directions for which no lattice point intersects this cylinder. And there you already see how the cylinder comes in. But now it's very long and very thin. So we apply a few linear transformations to the whole picture to make that cylinder nicely proportioned. And the key thing is that this cylinder no longer depends on rho. Of course, the trade-off is that now our lattice depends on the initial direction and on rho. Now the initial direction is random. So what do we get? We get a sequence of random lattices with respect to our random measure on the set of directions. We get a sequence because we are interested in rho going to 0. So the way I think of this now is I think of this as a random point process. We're trying to understand the properties of this random point process. We're trying to understand how many points are in this test set, which is now fixed. And we're trying to understand whether this sequence of random point processes has a limit distribution. Now in this case, of course, this language is a bit overkill because we can reduce it now into a question of equidistribution in the space of lattices. So this is what I just said. We are interested in this particular lattice with V random. Now you can identify, as I mentioned, the space of lattices with a homogeneous space, G mod gamma. G is SLDR and gamma is SLDZ. And so let's just take a test function here in this space. That was my homogeneous space. And ask exactly what happens when we integrate or average V with respect to our probability measure, lambda. And this equidistribution statement tells you that this average converges to the Haar measure. Okay? And why this is so follows from equidistribution of large spheres in this space, which you can derive as a result of the mixing property of this flow, phi t. So we haven't used Ratner here. And therefore, we get our theorem. Why? Well, just take as your test function f here the characteristic function of the condition that there should be no lattice point in that particular cylinder. And then you're done. Only problem is that this function is, of course, not continuous, but you can use some measure theoretic arguments. And you need to do some estimates to prove this. But this is, again, the technical step. So morally, you just take f to be the characteristic function of that particular condition that you wanted satisfied, and you get your limit theorem. Now, when we want to prove the full theorem, shooting off from a generic point, we actually need Ratner if we insist on fixing that generic point. But let me not go into detail. Exactly what I said. Not a rational multiple of a lattice point. So it's not just almost every. It's, yeah. But as I said, what I really want to point out is what we're going to do next with the quasicrystals. We really need Ratner even for the physical statement which we're initially interested in, when we didn't fix the initial position but allowed that to be random. Before I go there, here are some plots. So we only have explicit formulas for all these distributions in the two-dimensional setting. In 3 dimensions, we don't. And these Andreas computed. So we have, of course, now a formula in terms of measures. So we need to integrate this numerically. There's no other way we can do this at the moment. But you can do this very effectively. And that's how these things look like. On the left is the distribution, the density of our limiting distribution when we shoot off from a generic point. When we shoot off from the center or from the origin, we get this compactly supported distribution. I'm just showing these to you. I don't want to discuss this in details. I need Ratner? Okay, I need, so when I'm, no, let me make it very clear. Let me make it very clear. We can prove that whatever point we shoot off from, we have a limit, and we know what that limit is, and we need Ratner for that. So from any, not just generic point, any point you want, any initial position, we can prove that the free path lengths exist. Now,
This I understand.
and we have a formula.
Then the question is, when do you and when do you not need Ratner?
Okay. If I shoot off from a generic point in the sense of measure, I don't need Ratner. Yeah?
That clarifies.
Ratner is a complete structure for every dimension.
Mm-hmm.
And generic is a weird word that's used there to say there's sort of the biggest measure, and that's
Yeah.
As long as it's
every.
Yeah.
Every.
yeah.
It's every with an understanding.
But as I want to highlight,
That's why it's useful to remember.
yeah. Okay.
No, I'm confused.
Yeah.
For a generic point, I mean, distribution depends on the point or doesn't?
It doesn't.
It doesn't.
And generic and even in my sense, okay, even in the sense of not being a rational multiple of a lattice point.
It doesn't depend on the Diophantine properties of it, other than one clean statement.
Yeah. So no Diophantine conditions in the sense of badly approximal or something like this we need. So it works really for everyone.
It's not effective.
Of course. Of course, it's not effective. Yeah. Which is one of the big open questions in the field that people are now working on very actively. Rates of convergence. Yeah. Right, so the interesting feature of these limiting distributions, and that was already observed by Bourgain, Goltz, and Wennberg, is that they have an polynomial tail rather than an exponential tail as the random scatterer configuration. In fact, as you see from here, this distribution doesn't even have an expectation value, okay? This is the density. Now, before you get too concerned, the distribution of the free path lengths between consecutive collision is exactly the derivative of this. So this goes like psi to the -3, and that has at least an expectation value, but no second moment. OK, that's just a feature of what we have here. So now what about other scatterer configurations? And let's study the quasicrystals. And quasicrystal is a general word. Let me just check the time here. And I'm not sure if even physicists have agreed on what is a quasicrystal, because originally, of course, they were discovered by certain regular diffraction patterns that couldn't be explained by the usual crystal symmetries. But what we're going to study here is a large class of quasicrystals that can be constructed by the so-called cut and project method. And a famous example of families of quasicrystals that arise from this method is, for instance, the Penrose tilings. OK, so how do we do this? Well, suppose we want to construct a cut and project set in RD. What we do is we extend our space to Rn. So we have an auxiliary space Rm here, and we denote by pi and pi internal the orthogonal projections onto these two. Now then we're going to take a lattice in the big space in Rn, and we put it in there in some generic way. So we don't want it to align with the coordinate axis here. Like, we don't want to use the cubic lattice, because then we would have trivial projects in all directions. We want it to be sitting in there generically, so that the projection onto RD is dense in some way. And then we're going to filter out a few points, because we don't want to have a dense set, but we want to have a discrete point set. And this is done in the following way. So first of all, let's look at the projection onto our internal space and look at the closure. This will be some abelian subgroup, and we'll have some Haar measure on it. And then, so the way you could think about this is simply think of it as being equal to Rm. If you orient your lattice in a nice generic way, it will be equal to Rm. We're just going to do this because there are some interesting cases, including the Penrose tiling, for which it's not going to be Rm. But forget about this. Just think of A as being Rm. Then you choose a window set in Rm, and you're only collecting those lattice points that whose projection falls into this window set. So you mark those, and you project them down to your physical space, Rd. And that will give you a cut and project set. It's written down here. Okay? So that's exactly what I've just described to you in words. And now we're going to take this cut and project set as the locations of scatterers in our quasicrystal. So here's the famous Penrose tiling. And De Bruyn was the first who realized how you can construct such a tiling from a cut and project method that I just described, because before there were local rules and people sort of constructed them in different ways. So the features of such a cut and project set is it's a de Lorentz set, so it's uniformly discrete and relatively dense in Rd. Uniformly discrete means that no points can get arbitrarily close to each other. So when you have a Poisson process, that wouldn't be uniformly discrete, for example. And relatively dense in Rd, so that means that you find a large ball, so that wherever you put this ball, there'll be at least one point of your set in there. And a Poisson process also doesn't have this property, because you have arbitrary long, large patches. The set of primitive lattice points doesn't have this property, because you also can have arbitrary large patches, for instance. So this is a lattice has this property, right? That's a lattice is the prime example of such a set. And secondly, we also know how many points of our point set are in a big ball of radius t, and it's exactly proportional to the volume of that ball, with some constants that depend on our construction. So that's good, right? We don't want to construct a Lorentz gas whose density is sort of going to 0 at infinity. We want it to be homogeneous in this setting. Otherwise, these are consequences. This is just the only definition that I have. No, I don't know. I don't know. Maybe there are. Okay, and now here's the analog theorem of what I showed you before, which is simply to say, well, the free path length exists. Okay, that's already a non-trivial statement, as you all appreciate, because it could not exist, right? It could oscillate around, could have different limits, could be some escape of mass. It exists, so we have that. But now the question is, of course, what is the limit? How does it look like? How does it depend on the initial point, for example, and all these things? And as you've already realized, there is again a lattice sitting in the background here. And of course, that was why we started with this, because we can now again hope to apply the same tricks as before. And I emphasize, there's really no new idea here. The only thing is that the problem is getting harder and interesting at the same time. So that's was our justification to study this. Now, in analogy with the space of lattices, we call this now the space of quasicrystals in the following vein. So remember, what did we do before? We had our lattice, and then we were deforming it by linear transformations. So now we want to do the same thing. We take our quasicrystal and we apply SLDR to it. Yeah, that's right. Okay. So in the previous theorem that I showed you, shall I come back to this when I discuss Ratner? Yeah, I'll come back to that when we look at the equidistribution problem, because as I mentioned before, we didn't even use Ratner for the most of the setting, but I'll get back to this. So what do? We rotate it, and we pushed everything together to get our test set, which was long and thin and in a sort of random direction, to become a fixed test set. And this was achieved by applying SLDR rotations and this dilation. And now what we want to do now is we want to understand how this SLDR action acts on our big lattice, because now we have embedded everything in Rn. So we want to embed this group, SLDR, in ASL NR, which parametrizes the space of our big lattice that we use in the construction. Okay, and now Ratner tells us, and this has nothing to do now with equidistribution or unipotent flows, Ratner's theorem spits out that you can find a close connected subgroup, Hg, in G, so that A, the intersection of our big lattice, ASL NZ, with Hg is a lattice in Hg. And this has the consequence that Hg modulo this space is again a nice homogeneous space, which is embedded in our big space, ASL NR modulo ASL NZ. So it looks like some embedded submanifold in this space. And this embedded space will become important because that will carry our probability measure that we use to understand the distribution of the free path lengths. Now, second, the embedding, the image of SLDR under this embedding is contained in Hg. Okay. And the third property is that the closure of our embedding in this space of this orbit is given by exactly the embedded orbit of our closed connected subgroup Hg. So this thing is exactly what I described in there. This is isomorphic to Hg modulo gamma intersect Hg. Okay? So here's the picture that you have to have. We have our image of SLDR in our big space of lattices. And we look at its closure. And we understand that the closure of the image of SLDR, this very thin thing, is a very nice closed submanifold in the big space. Okay? It's like think of looking at an orbit of a dynamical system, and you understand that it actually fills out a nice submanifold in your big space. That's exactly what this means. What? D is greater or equal to 2. Absolutely. Yeah. That's an intrinsic assumption in all I'm doing, because if D is 1, the Lorentz gas wouldn't be very interesting. Right? Yeah, absolutely. So that's really crucial here. D is greater or equal to 2. And now we use the harm measure of our group Hg, and we find that it's a probability measure on this. I mentioned this before. One can show, and that's what Ratner says, is that indeed this thing, Hg, this thing is a lattice in here, means that there's a finite measure, and that comes from the harm measure on Hg. So that's observation number 1. Okay? Now we want to somehow understand how this space Hg now I want to understand how the space of quasicrystals that you can somehow think as a closure of your initial quasicrystal that we set off with under the SLDR action, how does this look like? So this is all as above. So this is our initial lattice that we use in our construction. And we represent it as Zn times G. We have a scaling factor here because this lattice initially might not have had covolume 1. So we just rescale it. It's not so important. And then here again, this group A is the projection of L, as we've defined it before. Now remember, this guy here was the closure of this SLDR orbit embedded into our big ASLDR. And what we can show is that the projection of all points in this orbit are contained in A. So that's good. We're not leaving our initial internal space. And secondly, for almost all points, H in there, we actually get all our internal space. So what this means in simple words is that we have constructed a whole family of cut and project sets, which are parametrized by this. And they're all, or almost all of them, have the same internal space A. Some of them might have a smaller space, but we don't care about them. Yeah, that's a consistency, right? I mean, we don't want to start off with one cut and project set, then generate a whole family of them, and having to vary A would be not so convenient. Wouldn't look good. Fortunately, it does all work out. Okay. And now I'm just going to, in analogy with a space of lattices, I'm going to parameterize, use my embedded submanifold to parameterize the set of quasicrystals that we obtained. So I'm going to call this then the space of quasicrystals. The reason why we like doing this is because, in some sense, we like to think of random point processes more generally. And each quasicrystal in our family will be a realization of this random point process. It's not a Poisson process. It's not independent. But there is a probability measure that assigns to each configuration in our family a certain weight. And that's just given by Haar measure. So this will be my space of quasicrystals endowed with a probability measure. That's just the push forward of our Haar measure on this space to these point sets. And now you see, once you have appreciated that, we have a very simple formula for the distribution of free path lengths. And that is just to say that the distribution of free path lengths in our initial fixed cut and project set is given by the probability that a random cut and project set in our space intersects the same cylinder as before in no point. So it doesn't intersect the cylinder as before. In the periodic setting, we had the space of lattices. Now we have this other space. But of course, the question is, what is this? What is Hg? Okay, I haven't discussed at all what Hg could be, except to say that it has nice properties, so that if you intersect it with the modular group, it'll be a lattice in Hg, and so on. So it has all the good properties that you like. But how do they look like? So here are a few examples. So the first is that if we take a generic, in Tom's sense, lattice, generic and measure, that we use for our cut and project construction, then the group Hg will in fact be the full group. If the point is in, so this is not, so if we would shoot off from a generic point, it will be the full group ASLDR. If we shoot off from a point in our quasicrystal, as discussed before, it'll just be SLNR. And again, this limiting distribution then you can see from the representation in terms of our space will be independent of Q. And this is a non-trivial statement here because there's no longer translational symmetry as in the lattice, right? In the lattice, the origin was, of course, equivalent to any other point. Here, it's no longer the case because you move upwards. And then here, this is the other question. If we have this generic point, again, in the measure sense, then we get the full group. So we have this. In this case, we can show that, again, the free path length decays like psi to the -1, just as in the case of lattices. And the other properties also become apparent from the formulas. Now, but the really interesting case is not this, okay? The really interesting case is if we look like Penrose tiling, for example. So when we do that, then what we show is that Hg, our group, so now the Penrose tiling essentially comes from a construction in R4. It's not quite true. It's actually coming from R5, but it's only a sort of finite extension, something that lives in R4. Let's just think of R4. So in our construction, we use R4, say, for the Penrose tiling. Penrose tiling is in 2 dimensions, so our physical space is 2-dimensional, our internal space is 2-dimensional. And what you can show is that the way the Penrose tiling is constructed using algebraic numbers, the group Hg is SL2R squared, which is embedded in SL4R, just as blocks. And if you intersect this group with gamma, you'll find that the the lattice that you get is actually a Hilbert modular group, where the ring of integers that you're using in there is exactly related to the algebraic number field that you use in the construction of the Penrose tiling. And that should be a 2, of course, here. And similar construction work in, for all other tilings, also in higher dimensions, that are constructed from algebraic number fields. And this got us very excited when we found this, because I don't think people in the quasi-crystal literature have discovered the fact that actually the Hilbert modular group is a nice renormalization group for these Penrose tiling. Maybe they know it, but we've never seen it used anywhere. And here it comes up very naturally. Now, what we want to do, we haven't come round to this, is to understand the Taylor asymptotics of the distribution of the free path lengths. And this will be very nice, because you will have to understand how the particular test function that we're using here grows in the cusp of this Hilbert modular group. So I think that will be a nice calculation to do. Now let me just check. There's no clock in here. So forgive me for, I'm not checking if I got a new message. I'm just looking at the time here. So it's 4 minutes. It's there. I've got 4 minutes. I'm not going to go through all of this. I'll just tell you the result. That's something, it's a small observation that we've just made now. Well, so far we've seen in these very regular constructions using lattices, quasicrystals, that the free path length decays very, very slowly. So you can ask the question, what happens when you superimpose different lattices? So you take the union of 2 or 3 lattices, and you can again use the same machinery as before to prove that the free path lengths exist. Now, and if these lattices that you superimpose are not rationally related, what we can show, again using Ratner, is that the limiting distribution actually becomes the product, for the limiting distribution for the free path lengths becomes the product of the individual distribution of our lattices. Okay, so we want to have the union of our lattices to still have density 1, so that means we assume that each individual lattices has a density smaller than 1, say n bar 1, n bar 2, so that all the n bars sum up to 1. And then you see it cropping up here. So this is the free path lengths distribution that we've seen in the beginning of the lecture for an individual Euclidean lattice of covolume 1, and it's just scaled here by the free path length, and it becomes independent. And that means that we have an example here where we can obtain any power you want as a decay rate for the free path lengths. And that's just the key observation that we wanted to make. And as I mentioned, Ratner again helps us here. What you need to show is that for incommensurable lattices, the SL2R that is diagonally embedded now in the product of SL2Rs becomes uniformly distributed everywhere. And that gives you the independence, because that then means that the limit measure is a harm measure on each factor, so everything's independent. But I don't want to go back into this. I want to conclude by addressing Peter's point, because I still haven't said that. Why do we apply Ratner at all? Okay? Why can we apply Ratner? Well, the reason is that we're looking at these spherical averages. And it is a fact that you can approximate the spherical averages by horospherical averages. And the horospheres are generated by unipotent orbits. And Ratner gives us a classification of all ergodic invariant measures under unipotent flows. Now, as we look at larger and larger spheres, you say, well, let's assume we have a limit, right? Rho tends to 0, so we get this sequence of spheres that are expanding. Because they become close to unipotence and they become longer and longer, you can show that any possible limit point has to be invariant under unipotent. And then Ratner's theory gives you a complete list of all supports of measures that are invariant under unipotence, and they sit on these nice embedded homogeneous manifolds inside. So that's the reason why we can apply Ratner. And let me just say, this again is just examples of how you can treat certain point sets. They're all derived from lattices. And what I'm really interested in understanding is there any natural random process that doesn't come from a construction like this? And I mean in a very general sense. We, of course, also understand when you take unions of a Poisson process on a lattice. We understand that. We understand what happens when you remove points at random from a lattice. This we can all deal with the same machinery. But is there a natural point process other than the Poisson process, which, for instance, is SLDR invariant? It doesn't come from a lattice construction like this. Because if you had such a process, you would get another example of a generalization of the linear Boltzmann equation. Let me stop here. Thank you.